Alexey Garber, who will talk about spheres with k-points inside. And it's going to be short today.
Yeah. Thank you, Adam. Thank you, Boris. Thanks everyone for being here. Or in Zoom. So this is a joint work with Herbert Edelsbrunner and Morteza Sagashan from IST Austria. So am I visible or that's fine?
That's fine.
Okay, yeah. So yeah, and I'm going to talk a bit about spheres with k-points inside. Feel free to interrupt me, so it's probably slightly shorter than an hour. So I have time to answer questions on the go, hopefully.
We like short.
Yeah, it's relaxing. Okay, so before I start, let me start from the main topic or main object that I'm going to study, not what I want to do, but what are the things that I want to study. So there are going to be two main point sets. So I will start from point sets, and then I will have some simplices with vertices and these point sets. So it's a little bit more about computational geometry, but the underlying stuff is kind of combinatorial. So discrete geometry. So two objects that will be interesting for me are either finite point sets in d-dimensional Euclidean space, so just points, clouds of points, or what I will call thin Delana sets. So what are thin Delana sets? So, and surprisingly, those sets that have infinitely many points, they are much better for the topic that I'm going to discuss. So that's why I kind of emphasize that they are infinite. Finite are not enough. Infinite is a little bit better here. So thin Delana set is a set, any set that is roughly discrete. Well, roughly is doesn't have any meaning here. So it basically means that every ball contains finitely many points of those, probably 0. So there are no accumulation points. And second condition, that every half space contains at least one point of the set. So what does that mean? It means that there are no accumulation points. That's the first condition. Second condition, that there are kind of no very large empty regions, and very large means half spaces, right? So there is also notion of just Delana set, right? And that's a set that's sometimes used to model atomic structure of any objects, right? So that's kind of a little bit more restrictive in two cases. So first condition for Delana set is that minimal distance is bounded from below, bounded away from 0 from below by a positive number. And second condition is that there are no large empty voids. So kind of, yes.
So just to make sure I understand, there's no, this is for balls of every radius?
Every radius.
So this immediately kind of forces arbitrarily large distances, no?
No.
Oh, so pairs
finitely
of
many.
points can be, yeah. Okay.
Yeah, finitely many. So the best example of the set that's not going to work for me is, for example, set of points with integer coordinates. Every ball contains finitely many points, and there are no empty half spaces. Right? But it doesn't work for me because I want my sets to be generic. Right? Arseny, you have a question? Complain? Okay, so my point sets are going to be generic, so that means that no d+1 points are on the same hyperplane, which means every d+1 points create a simplex for me with the vertices in that set, and no d+2 points lie on the same sphere. And that's because the talk is going to be about spheres, so that's to make sure that I know how to count points inside, right? Because if points on the boundary, it's unclear.
Those conditions, are those alternate conditions or simultaneous?
Which
The generic, what you
the
call
generic, both of them. I require
You
both.
want both simultaneously?
Yes, both at the same time.
Okay.
Okay. So why do I need these? So why do I need why am I interested in these sets and why do I need conditions? So because in that case, there is a very nice triangulation, which is called Delana triangulation. And it is spelled differently, but that's the same person. Right, so that's Delana triangulation, that's the same person, but it's Delana. The reason why there are two different spellings, and it's actually different in even all the papers. So if people write papers about Delana triangulations, they use that spelling. If they write about Delana sets, they use the second spelling. And sometimes if people write about both, they don't know that that's the same person. The reason is that he was Soviet mathematician of French descent, and he was writing till I think 1930s. He was writing papers in French and used French pronunciation. After that, he was writing papers in Russian, and it was just transliterated to English. So that's why there are two different spellings of the same name, but that's the same person. And this construction of Delana triangulation is based on his 1924 talk at International Congress in Toronto. So it's called the talk, and the paper from the paper, I think, was in 1934, was called on empty sphere, and that's kind of connected to the title of that talk. So the construction is the following. So if we have a finite point set or a thin Delana set in d-dimensional space, and here I already use properties of the generic property. So if I consider all simplices that satisfy the following property. So if I circumscribe a sphere around that simplex, and this sphere is well defined because it's always a simplex, then if that simplex is this sphere is empty, so there are no points of the set inside, then I'm going to include that in my collection of simplices. So then this collection of simplices form a triangulation, either of the convex hull or of the whole space. And here's an example. So this is my point set. If I consider all two-dimensional, all pictures are going to be two-dimensional. So if I can consider all triangles with empty circumcircles, then I get this triangulation of the convex hull. And it's not obvious why am I going to get a triangulation. First of all, it's not obvious why every point will belong to at least one simplex or at least one triangle, why at most one. So the proof of that I like the most is the following. So if I consider the following lifting construction, all right, so I'm going to lift every point of my set on the standard paraboloid, so y equals sum of squares. Then I consider the convex hull of the lifted points, and the boundary of that convex hull. For the finite point set, I need lower boundary. For the whole set, I can just take the whole boundary and project it back on the d-dimensional space. Then I'm going to get that triangulation. And the reason for that is the following. So if I have the convex hull and I have a facet of that convex hull, so which is supported by a linear equation. So it's that means that in addition to that equation over here, so y equals sum of squared, I have a linear equation, so I make them equal. So I have sum of squares equal to linear equation. So that's equation of a sphere. Right, and all the points, since all other points of the set are below, above that hyperplane over here, that means that they're going to be projected outside of the projected sphere or circle in the two dimensions. So that's a very nice geometric construction that doesn't require anything beyond one equation. So why those Delana triangulations are so interesting? Yes.
No, just
and why they are so useful? Well, that's my favorite way of saying. So if you need a triangulation for some reason and you don't have too much expectations from that triangulation, like you don't want to restrict it too much, then there's a good chance that Delaunay triangulation will work for you. And they are used in, I don't know, hundreds of applications, starting from computer graphics, pathfinding, cryptography, and so on and so forth. Okay, so that's kind of the motivation that is related, but not really related. So here's the real motivation. So it's kind of known what we can do with simplices that have empty circumspheres. So the question that Herbert Mortez and I was trying to think about, okay, what about simplices that have circumspheres with more than 0 points inside? And we call them k-hefty simplices. So if we have either finite or a thin Delaunay set in d-dimensional space, then we consider collection of all simplices that have exactly k points inside their circles. When k equals 0, we get simplices of Delaunay. When k is greater than 0, we have more simplices. They actually also appear in computational geometry, particularly in constructions related to Voronoi diagrams and higher order Voronoi diagrams, but I'm not going to go there, at least not now. So the question is, what can we say about these simplices? So do they have some nice properties that resemble Delaunay triangulation? And the answer is, well, we don't know right now, not at this moment of the talk, but let's try to understand what we can find out, since it's already way past noon, so it's time to play some game with those points. And I'll try to do that in the simplest case which is possible, or at least which is interesting. So d equals 1 is not that interesting, because for d equals 1, k-hefty simplex means, so for d equals 1, we have points on the line, and k-hefty means that we have k-hefty simplex is a segment with k points inside. So we can say whatever. So we know what are the simplices. We can have a lot of information about that. Similarly, so it means that d equals 2 is the first interesting case. When k equals 0, we know that we're going to get Delaunay triangulation. So k equals 1 is the first interesting case. So d equals 2, k equals 1. And the question that I'll try to answer is the following. So suppose we have an arbitrary point that doesn't belong to the set. So that point is not inside the set. And we want to find out how many triangles, how many one-hefty triangles of A contain that given point. And apparently there is always a certain number. And let's try to find out, right? So first of all, we know that all triangles that belong to Delaunay triangulation will not work, but that's a good start. So let's start from that only triangle of the Delaunay triangulation that contains this point. And since we're interested, so this is a 0 hefty triangle. Since we're interested in 1 hefty triangles, this will not work, but 0 and 1 are kind of close to each other, so maybe they are related. So let's try to try the following process. So
but it depends on the point set, right? It's not is it with respect to this set you're asking, or in general?
Yes, with respect to that set. So how many and what are they?
The game that he has in front of us.
Yeah, but I mean, yeah, okay, just to making sure it changes according to the point set you chose. Okay.
Right, but we fix 1 point set and we try to understand how many of the triangles. And that's a good question, because the number may depend on the set.
In convex position, there should be 0, right?
Okay, we'll see.
Okay, I'll wait.
Yeah, so what we can do, we can take 1 point of that set, 1 vertex of that triangle, that one, and remove it from it. So then this is a new set. For this new set, we still have a Delaunay triangulation. And this Dellan triangulation has a triangle that covers that point. Well, assuming that this point is not very close to the boundary, right? So assuming it is sufficiently deep inside the set, and this triangle will work. And the reason for that is that this triangle that cannot have empty circumcircle because it was not in the original Dellan triangulation. So it must have at least one point of the set inside, but it doesn't have all other points or all other points over here. So it may have only one point, it's exactly one. And we can repeat that process with the second vertex, with the third vertex, and overall we will have these three one hefty triangles. And there are no more. And it's possible to prove that because if there is a one hefty triangle, then it should have exactly one point inside circumsphere. So if we remove it, then it should be a Dellan triangle of the set with removed point. But if we didn't remove one of the original 3 points, well, that triangle must stay there. So this is the only these are the only 3 triangles, and that works for set in the convex position as well.
Yeah, I see a mistake.
Yeah, but that's a good question. So here we have exactly 3 triangles for every point set. For d-dimensional case, we will have exactly d plus 1 simplex, right? So the number of vertices. And that kind of gives a hint, or at least a hope, that if we do that for arbitrary d and arbitrary k, so maybe there will be some constant that theoretically may depend on the set, but and let me just put everything on the table so it does not. So that's our main theorem, that if we have a thin Dellan set in d-dimensional space, and we have a generic point in d-dimensional space, then that point belongs to exactly d plus k, choose d, k hefty simplices. So this constant doesn't depend on the set, it depends only on the dimension and on k. And here's example for d equals 2 and k equals 2. So there are exactly 6 2 hefty triangles. So this is a 2 hefty triangle, and it's actually not that easy to decode what are these 6 triangles from that picture, but there are exactly 6 of them. So when k equals 3, there are going to be 10, and that's impossible to see it. And already here it's kind of possible to see why do we need thin Dellan sets. Because if we're dealing with finite sets, then boundary will mess up everything, or at least something. Because if I would try to construct well, either 1 hefty triangles or 2 hefty triangles for a point which is next to the boundary, so then after I remove that point, then there will be no 1 hefty triangle, right? Because it's already outside the convex. So with finite point sets, it's not going to work. Still, something is going to work, and I will tell something about that. Okay, any questions or objections? Okay, so how can we prove that? The proof will, well, that's kind of the main proof that I'm going to tell you, but there will be a few minor proofs as well. So the proof is actually in 3 steps. So first, so we can think of that theorem in the following way, that if we consider all k hefty simplices, then they cover the space, d-dimensional space, in certain number of layers. It's not completely correct to say that, because when we say layer, we usually think that we can kind of split the triangles into actual layers. That's not true. That's not always possible. But roughly speaking, so if we try to poke a hole in the space in a generic way, so we will not poke the boundaries of simplices, then we will always poke d plus k choose d simplex. So that's the meaning of the theorem. So and the proof is the following. So first of all, that if we fix a set, then I'll prove that we can have that constant covering constant covering number, right? So that the space is covered in fixed number of layers or fixed thickness, let me call it like that. The second step of the proof is to show that this actual constant doesn't depend on the set, right? So for every two sets, the constants are the same. And the third part is I can just present a thin del in a set where the constant is somewhat obvious from combinatorial reasons. Okay, so the first step, and for the first step, I want to show that there is a covering constant. So in order to do that, what I will do, I will show that if I start to travel from a certain point and will travel around the space, then the number of k-hefty simplices that cover the point in which I travel doesn't change. And when can it change? It may change only if I cross border of a simplex and I leave certain number of k-hefty simplices, but I enter a different number of k-hefty because everything is discrete, right? And suppose that happens, so there is a simplex or collection of d vertices delta, so d is 2 here, so that's my facet delta, which is facet of a k-hefty simplex. And if I travel along the space, when I travel across that delta from left to right, I kind of assume that this is vertical, then there are different number of simplices on the left-hand side and on the right-hand side. So what does that mean? Well, I consider the perpendicular bisector, that line is the perpendicular bisector, and I just force the center to travel across the perpendicular bisector. And for every point, I write down how many points of the set I have inside. And that information allows me to say when I have k-hefty simplices on the left and on the right. So I have, so since when I travel from here to the right, the part of the sphere to the left of my simplex delta is actually it shrinks. So that means that if I change the number from k plus 1 to k, so that means that I go through a point and there are exactly k points inside the circumsphere here. So when I travel from k plus 1 to k, I pass through a k-hefty simplex that is on the left. And similarly, when I go from k to k plus 1, I encounter a k-hefty simplex on the right. But since I'm dealing with the thin del in a set, so I have an infinite number of infinite number of points here, infinite number of points here, right? So there are equal number of transitions from k plus 1 to k and from k to k plus 1. So that means that on both sides I have the same number of simplices and there is a covering constant. So that's the first step. The second step is to show that the constant is the same for all sets. And I can do that the following. So there is a technical lemma that is not here, not on the slide, but basically it says that in order to find all k-hefty simplices that cover a certain point, I need to look in a ball of finite radius. So all the points cannot be far from each other or infinitely far. So there is kind of some local picture that explains everything. So I take two sets, I take one huge local ball from one set, another huge local ball from the other set, put them together far apart, and just sprinkle points around to make sure that I'm dealing with thin delegates. And that's enough, right? Because I have certain constant here, I have another constant here, but since I can turn them into common thin del in a set, the constants must be right? So that's the second step. And the third step is just to show that it is a binomial coefficient, that it is d plus k choose d. And to do that, we can just find one set where it is d plus k choose d, and this is what we call the radial thin Delana set. So we take a regular simplex, and starting from the origin, we just multiply all vectors by positive integers, right? So we have d plus 1 raised with kind of equally spaced points. That's not generic, but we can perturb it a little. And in order to find, and we don't need to find the constant for that set. We need to find constant for 1 point of that, 1 point using that set. So for the origin, what is a k-hefty simplex? That's actually a simplex that has vertices on every on every ray, right? Because that's the only way to cover the origin, and the number of points on the rays inside the simplex must be k. So we need to put those k points from the rays into d plus 1 boxes that correspond to the rays. And there is a combinatorial, that's a very nice exercise in basic combinatorics, that there are d plus k choose d options to do that. Right, so that's the end of it. So we also have a version of that theorem for finite sets, right? So, and as I said, we cannot get exactly the same result because the boundary is cursed. We can.
If the point lives on sphere, then.
What do you mean on sphere?
Yeah, we have a three-dimensional sphere and we have.
Wait a little bit. Wait. So yes, there is a similar result for spheres. Yeah, but for spheres, because we don't have everything Delana set is finite. So, but for finite sets in d-dimensional Euclidean space, the first thing is that we have at most that many simplices covering the point, covering any point. But also if the point that we want to cover is sufficiently deep inside, and sufficiently means that, well, it is sometimes it's called K convex hull. So that means that if we remove all possible subsets of K of size K from the set and take intersection of the convex hulls, or which is the same if every hyperplane through that set has at least K points on both, at least K plus 1 points on both sides. So then we have still exactly d plus k choose d k hefties. And ID is very similar that we use in the proof. So we basically sprinkle more points around to get a thin Delana set, but to make sure that we don't add k hefty simplices among the initial points. The result, so this is what we call the global results, because every point is covered exactly that many times. We also have a local result, and for local, I mean here that we're considering only k-hefty simplices that are incident to 1 point, right? So we fix 1 point of the set of the initial set, and we consider only k-hefty simplices that are incident to that point. So then they are not guaranteed to cover anything far, but they cover everything locally. So that's why I call it local version. And they cover everything locally also in the binomial coefficient times. So d plus k minus 1 choose d minus 1. And as Arseny kind of asked, so that's so he didn't ask that particular, but that's could be related to properties for similar coverings on the sphere, because this is kind of considering one dimension, so decreasing dimension by 1, right? So if we consider a small sphere around that point and use, let's say, stereographic projection, then it will go to 1 dimension smaller, right? So it is related to covering on this. But there is a simpler proof. So, and simpler proof is just taking difference between two binomial coefficients. So let me write it down here. So this is just for all k hefty simplices. So the idea is that we consider a point close to the chosen one, right? Then the total number of k hefty simplices covering that close point is d plus k choose d. But if we remove that original point from the set, then there are going to be k minus 1 hefty simplices. So these are k minus 1 hefty simplices without a point, so without the selected point, right? And if we add it back, then they will become k hefty simplices that are not incident to that point, and the remaining must be incident to that. That's that's the idea of the proof. Okay, so these were kind of main results. So, and I still have some time, so we really liked that because, well, that's kind of generalization of result of Delano that is used everywhere. So we tried to apply it at least to some theoretical questions. We were able to recover several results. So what I'm going to kind of show now are two applications. So first application is to k-sets. So it's still about computational geometry. The second one will be a little bit about algebraic combinatorics. It's two Eulerian numbers. So how we can recover some properties of first k-sets and then Eulerian numbers. And then I'll talk a little bit more about spheres, as Arsenia asked. Okay. So first k-set. So what are k-sets? So suppose that we have a finite generic set. So now we're dealing with finite sets. Actually, it's not k-sets, it's k-facets that I would be interested in. So a subset of this set A is a subset of size D, and it's called k-facet if the hyperplane through those D points cut exactly k of the points from the set. So on one side, there will be exactly k points. And it's a classical question in computational geometry to give bounds on the number of k sets. So if you have a set of size n and fixed k, how many k sets or k facets? So k set is just the points that we cut. So in here is k facets. So how many k facets could be? Upper bounds, lower bounds, extremal cases, what can we say about that? And the connection between the, so at first it looks like it's not connected, right? So I have spheres and here I have hyperplanes, but after we perform an inversion, then every k facet turns into k hefty simplex, right? So if I start from a 2 facet here, so these are 2 points that are on that side of the hyperplane or plane here, and it doesn't matter what is on the other side. So if I perform an inversion with that center, then it turns into a 2 hefty triangle, right? So these 2 points will turn into these 2, and these points will move inside the circle or inside the circle. So every k facet turns into a k hefty simplex for the new set A and O, right? So where I add additional one. So k facets are related to k hefty simplexes, and we were able to recover two results about k facets. So first, a two-dimensional result by Alon and Diorin. So if we have a generic set in the plane with n points, then the total number of 0, 1, etc. k facets is at most k plus 1 times n. And the bound comes from points in convex position, n points in convex position. So then every 0 facet is just side of that polygon. every one facet is diagonal that connects points, skipping one, so there are n such diagonals and so on and so on. There are exactly k plus 1 times. So, and they have a combinatorial proof, so here we have kind of geometrical proof. So for simplicity, we assume that k is at most n over 3. So in that case, there is a point that is deep inside the set, which is called center point. So we pick that point and we perform inversion with respect to that point. So then what happens is that we have this point O, and we have n angles from that point, and we want to count the number of I have t, not simplices, triangles incident to that point, right? And since there are n angles, we just count how many. So since those triangles must cover the neighborhood exactly k plus 1 times k plus 2 over 2 times, so that's just sum of binomial coefficients, then we count how many angles can we use, and well, the outcome is that since we can multiply by n, that's the minimal, the maximal number of triangles we can use. So if we use triangles that have one of those angles, or those that cover 2 angles, or those that cover 3 angles, and so on and so forth, up to I think k plus 1. Right? That's the idea. So that's the first result about k sets that we were able to recover. The second one is what is called Lovász lemma, or more specifically, the exact Lovász lemma that was proved by, so the original version was by Baran, Furedi, and Lovász in 1990. The exact version was by Velzel in 2001. So the lemma says that if we have a generic point set, and we have with n points, and we consider all k facets of that set, every line intersects at most d plus k minus 1, choose d minus 1, directed k facet. And directed means that we're kind of looking on which side the k points are. So we're looking only on the sets, on the facets that have k points on one of the sides. And this is dangerously close to the binomial coefficient that we had before for the local version. And that's exactly what we can do. So if we pick a point on that line that we want to intersect with k facet far enough and perform inversion, then all those intersected k facets turn into k hefty simplices intersected by a line or by a ray from O. And since the covering constant is d plus k minus 1, choose d minus 1, then it's a finite set, then we have this at most that many k hefty simplices, and that means at most that many k set. Velzel proof is about 10 pages with some probabilistic method.
Wow. So in your proof,
Well, as soon as we know the number, the constant covering number, then yes, it's like half a page.
and I thought it was like 5 pages.
Okay.
You think that's right?
With a little bit more, but yes. You still need the technical level. Okay, any more questions? Okay, so a little bit of algebraic combinatorics. So the result from algebraic combinatorics that we were able to recover, it's not really algebraic combinatorics, it's more about combinatorial properties of volumes of hypersimplices. So what is a hypersimplex? So it's a polytope of the order k d-dimensional hypersimplex. You can think of that as a slice of d plus 1 dimensional cube, right? So those are, so if we consider d plus 1 dimensional cube and standard 0, 1 cube, and the vertices of the cube with sum of coordinates equals d, then that's a d-dimensional polytope, and that's what we call order k d-dimensional hypersimplex. There are slightly differences in how you define parameters, so sometimes there's difference in dimension by one, but that's what I'm going to use. So it is known that the volume of that polytope is the number of permutations of the set 1 through d with certain number of descents. Also, if we just write them down and count how many times we know we're going down in that sequence. So that's what is called Eulerian number. And well, okay, I said volume. Correct way to say it is that it's relative volume, right? Because it's a lattice polytope, then volume is an integer number divided by d factorial. So kind of when we're doing that kind of computations, we usually ignore d factorial. The proper way to say it's that the volume times d factorial is Eulerian number dk minus 1. And initially it was hinted in the paper of Laplace from 1886. And that, as far as I understand, the proof is by induction, but I don't know 19th century French, so I will not vouch for that. But there's also a very nice combinatorial proof by Stanley from 1977. So where basically he constructed a way to represent hypersimplex's union of that many basic lattice simplices. So simplices with relative volume 1 over d factorial. So we can get a geometric proof using our constant covering number. And the way to do that is actually the same lifting construction that I used to construct Delaunay triangulation with slight adjustment that I want a slightly better set. So not just the arbitrary thin Delaunay set, but let's say a perturbation of the integer lattice, just to make sure that it is generic. So again, we lift all the points on the paraboloid. Then we fix the number n, and for every subset of the lifted set of n points, we take the average point. So we have initial cloud, then have cloud of averages, and then we take a convex hull and project the boundary back. So convex hull of the averages and project the boundary back to the d-dimensional space. So this is what is called the order n Delaunay triangulation. And the standard Delaunay triangulation kind of tells you information about which points are close, which original points are closer to the given one. So this triangulation tells you which n of the original points are closer to the given. Not precisely, but it's related to that. And the worst part of that is it's not really a triangulation, because it doesn't use simplices, it uses hypersimplices. So for given n, it uses hypersimplices of order 1 through d, and those hypersimplices originate from n minus 1, n minus 2, etc., n minus d hefty simplices of the set. And the way to see that is very similar to kind of how I constructed facets of the convex hull when constructing Delaunay triangle. So because if I have a linear function, then what are the vertices that will lie? What are the averages of endpoints that will lie on that hyperplane corresponding to that linear function that supports hyperplane that supports that set? So I need to minimize the value with respect to that linear function. So I need to take minimal values corresponding to the original points and minimal values. But I start from some values, and then in order to get full dimensional picture, I have to have a simplex, right? And depending on how many points I have below that 1 through d, right, I will have certain order of hypersimplex, and that many points, or I'm sorry, n minus 1 through n minus d, and that many points I will have inside the circles. So that's kind of simplified version. So I will have these hefty simplices participating, and I create these orders of hypersimplices. And now if I take the tiling of d-dimensional space, take a large ball and compute the volume of everything that is inside. And here I use that I started from integer lattice, so I have very small error in the computation, so I can take the limit. So then every simplex that I have, k hefty simplex, or in this case, n minus p hefty simplex, it contributes its volume, and its volume is the volume of simplex, right? Multiplied by Eulerian, or well, just volume. We don't know whether it is Eulerian numbers because I'm proving this Eulerian numbers. So it's volume of hypersimplex multiplied by the covering constant, which is this binomial coefficient, and divided by power of n, because I took averages. So 1 over n raised to the power d. Well, I take the limit, and since I used all those orders of hypersimplices, so this is after the limit and multiplication by n over d, this is what I'm going to get. So now Wikipedia helps because it says that this is very similar to Warpitsky's identity for Eulerian numbers, right? So it is sum coefficient times binomial coefficient. Sum of that is equal to power of n. Well, here it's power of x because it's equality for polynomials, but it's very similar. And after some argument, you can show that volumes here must be Eulerian numbers here. And the difference in one here, right? So remember, it was a d k minus 1. So here summation is from 0 to d minus 1. Here it's from 1 to d. All right, so that's how we can prove that volumes of hypersimplices are actually Eulerian numbers. Or actually, there is another way to think of that. We can think of that as a new proof of Warpitsky identity, but that's not that catchy, right? Or we can think of that as a second proof of our constant covering. Okay, so these are two applications, and yes, as Arseny noticed, there are different settings where this constant covering number will work. So it will work for hyperbolic space as well, with pretty much the same proof, with minor adjustment at the end, because that radial set is not a thin Delana set in the hyperbolic space, but we can still put some points around to make it work. For the sphere, it will work as well, but we need to be careful because when we consider a simplex, a spherical simplex, it may happen that we have a circumsphere that k points are in the bigger part of the sphere, and we don't want that to happen because we don't. It's unclear how we can say that this small thing around one pole covers the other pole. All right, so and to do that, the way we can make it work is to say that our set A has to be k balanced, right? So that means that in every hemisphere there should be at least k plus 1 points, and that's similar to the situation where for finite point set we have equality, right? So on both sides there are at least k plus 1 point. So here on in every hemisphere at least k plus 1, every open. So these what we call k balance set, and there are both global and local versions. And going back to computational geometry, there is also a setting for weighted point sets there, and I will not go into details, but it works here if we assume that weight is good. So for example, if weight is bounded, then the same proof works for the global situation. It doesn't work for local. So it's only global.